result. And then we'll have sort of the setup and then the solved separately. Okay. All right. Oh, here's a question. Yeah, if they're to swing back down to collide with each other, would the momentum be conserved then? Right. So yeah, you can imagine in real life if you kept going in time, right, that they would swing back. But you still can't really say momentum is conserved. The collision, so from the time right before they collide to the time right after they collide with each other on the way back down, we would want to use momentum conservation there, but not for the whole swing where there's external forces acting on them. Yeah, because if they come back down and they collided with each other, it's like the reverse of their push problem. So we use momentum for that push problem, right? We also use it for collisions. So it's like explosions and collisions are basically the same thing, just happening opposite ways. Yeah, so sort of accidentally, right? If their momentum is conserved, then everything would be symmetrical. Yeah, right. But it's not like fundamentally that momentum has to be conserved, right? That's in some sense an accidental conservation just because you set things up symmetrically. But even then, right, their y momentum goes away. So that would just be in the horizontal, that it would always be 0. But they first gain y momentum as the string, swung them up, and then they'd lose it to gravity at the top of their swing. Okay, so I want to go actually back to the problem. What were we trying to find? So now we need to use our formulas that we wrote down, right, for the 2 steps to relate what's going on in the problem. Yeah, and actually go over to solve. So eventually what we want to find is what height does Ed go, given that we know the height that Joe goes. All right, but let's start with the first part, right? So first we'll do the momentum conservation, right? So this is 1 to 2. Right, and so you can write out P1, right? So P1 is going to be mass of Joe times velocity of Joe at 1, right? Plus mass of Ed times velocity of Ed at 1. And I'm just going to do one velocity, right? It's that x component, that horizontal component, right? But since they don't start off moving at 1, right, these are both 0, right? And so this is just all 0. Then at 2, I have some different momentum where they are moving, right? And so I have mj, vj at 2, right, plus me, ve at 2. And in the end, I'm going to look ahead a little bit, that I know I'm going to want to find something out about Ed. So I'm going to go ahead and solve for Ed's velocity in terms of Joe's velocity. So P2 equals P1, right? So it also equals 0. Right, and so I can move Joe to the other side, and so divide by Ed's mass, and I get the Ed's velocity at 2 is just minus Joe's mass divided by Ed's mass times Joe's velocity at 2. Okay, then I need to bring in 2 to 3 because I can't go any farther. I don't know either of their velocities, right? That depends how hard they actually push, which I don't know. And so I'm kind of stuck for a second, but that's where I bring in the second part, right? So in 2 to 3, what we're going to do is we're actually going to think about them as separate systems now, right? And you can see that because, right, they're not going to have anything to do with each other. that the only thing that changes how high each one goes is how much kinetic energy, right, that they started with. There's no way for them to exchange their energy between them, right? And so I'm going to get a different formula for Joe and Ed. So if this is for Joe, right, I'm going to have the kinetic energy at 2 plus the potential energy at 2, right, is equal to the kinetic at 3, right, plus the potential at 3. For gravitational potential, which is the potential we're talking about, right, you get to pick where 0 is. Right, you get to pick a height that is your 0 of your coordinate. Right, so I'm going to pick that at the bottom where they're at 0.2. Right, and so then that'll make this be 0. Right, and then they have some kinetic energy because they have a velocity at 2. So we can put in 1/2 mv squared for that. And then at 3, the person has stopped. Right, and so at 3, there's no kinetic energy. Right, and so what you get is something like 1/2 m Joe, v Joe at 2 squared, right, is equal to m Joe's m times g times Joe's height that he goes up. So all that kinetic energy just goes into gravitational potential. Now you get the exact same formula, of course, for Ed, so I won't do the whole line, right? So 1/2 m for Ed is Ed's velocity at 2 squared, and that's equal to m Ed times g times Ed's height. Move this up a little. Okay. Now, each one of these equations tells me how the velocity at 2 is related to the height. Right? And then that's what I had from the momentum equation from 1 to 2, something about their velocities. Right? So I want to solve each one of these for the velocity, right? And so you get something that looks like all the masses go away here, right? And so you get something like Joe's velocity, right, is equal to the square root of 2 times g times Joe's height. And you get the same expression for Ed, just with e's instead of j's. So you can put that in, right, and you see that square root 2g Ed's height is equal to minus mj over me square root 2g Joe's height. The square root 2g's are the same on both sides, so those go away. And then I have a square root of the height. And so I can then square this, and I just get then this turns into Ed's height is Joe's mass squared divided by Ed's mass squared times Joe's height. And I kind of ran out of room a little there. Sorry about that. This was the old version of the problem. And then from there, you could actually stick in the numbers, right? There's like a 0.3 meters and then 110 squared divided by 73 squared. Okay. Yeah, can I explain again setting Joe and Ed equal? Yeah, I just kind of ran out of space here. This says that Ed's height is Joe's mass squared divided by Ed's mass squared times Joe's height. And I'll post the picture of this too if you want to check it later. Yeah, and so, and Adrian, so can you say your question? You wanted to re-explain setting Joe and Ed equal? I'm not sure I understood your question. Or you said thank you, so are you okay? Or if there's any other questions, feel free to ask. This was a complicated example and it's big, but it has all the stuff that we want to be able to do with momentum and energy conservation and different parts. Wait, who's Joe? Joe's just one of the guys that's pushing. Joe and Ed. That's their names. Okay, so if there's not more questions about that one, where were we? A couple other things to keep in mind when you do these problems, and it'll come up a bit with the other practice problems on the recitation.